All right. As I mentioned last time, your assignment number 1 has been postponed just for 1 week, but don't worry, you will still be given the same amount of time. It will be released next Monday. Okay, I'll make sure I do that, and then we can go over a little bit about assignment number 1 in the class on Tuesday. So you guys can take a look before Tuesday's class, and we can talk briefly. And I believe the slides are fixed now. So if you go to the lecture site, you will see that math review. If you click on that, right, the slides are there. So that basically contains all the logical foundation that we might need about the formulation for DFA, NFA, epsilon, NFA, and also later on when we study about the parsing algorithm. I think these logical stuff might also be useful. So take a look and then study them. And of course, as I mentioned, programming test wouldn't cover this. It's more like a conceptual stuff. But in the actual written test and also exam, they will be covered. All right, the stuff is there. If you want any clarification, let me know. And then there's also something I do want to mention. I kind of mentioned that on day 1, but I want to emphasize again. So for those of you who may want to do a little bit of work before the reading week, because as I said, for this course, before the reading week is rather quiet. But after the reading week, you guys will be given the projects and some assignments and also written tests, programming tests, etc. If you look at the calendar. If you really want to do some pre-study, after the reading week, assignment number 2 and also project will be released. And especially during the reading week, you will be assigned this particular tutorial video to watch, to learn about Antelope 4. So that one kind of shows you from scratch how you can use the Antelope 4 tool to actually generate parsers, scanners, and also implement your semantic analysis. Like a simple example. I'll show you where you can get them. It's actually been there since day 1. If you go to lecture site, it's actually right here. Using the Antelope 4 parser generator, if you click on that, it's actually a YouTube tutorial series right here. All right, so that's already there. For those of you who actually want to do a little bit of work before the reading week, you can feel free to take a look. Right here. Right, you can take a look. It's going to be assigned anyway, but if you want to watch that before the reading week, you're not going to waste any time. In some way, that can lighten your load a little bit. Well, I'll leave the choice to you. But if you only want to get started until you actually got officially assigned this tutorial, that's fine too. I'll leave the choice to you. And then you will also see some notes right here that's also just like a lecture style. Okay. All right. Guys, any questions about the course in general? Okay. And also for your programming test later, it's also going to be based on this Antelope 4 tutorial videos. Okay, just for your information. So I think that one there, if you can take some time, studying through it, digest the material, that'll be the best. Yeah.
Are all those videos relevant, or only the first 3?
Those videos, all of them are relevant. All of them. Yeah. Mm-hmm. Yeah, the entire series will be relevant to your assignment number 2, the project, and also programming test. Okay, all of them. All right, if no further question, let's now do a quick recap and then we'll continue. Okay. All right, so last time we started with this example here about given a language using the set comprehension notation, we want to define the DFA that's going to recognize just that language. Okay, so that's something we did from scratch last time. Just make sure not only they get a label the state names, but also you have to give some description about what the state really represent. And we did some more exercise about DFA, right? Things like contain 0, 1 as a substring. And we actually later on show that it would be maybe conceptually a little bit easier for you to specify using not DFA, but also by NFA, by using non-determinism, right? So NFA, DFA, they are really equivalent notation for expressing regular languages. But today we're going to see how you can convert from NFA into DFA by using something called subset construction. Right? That might be something you have seen already in 2001, but we're going to review that too. Okay? Given arbitrary NFA, you will be able to convert it into the equivalent DFA. Okay? That's something we're going to see today. Okay? And this page here is about formulation of the DFA. So each DFA is a machine And then you got the set of states, you got alphabet, you got transition function. And for this one here, I'll guide you to maybe the math review lecture to see the difference between function, like a total function versus partial function. Right? That's a study question for you guys to look at. And this will be initial state. We assume that there's only one start state, but there could be multiple final states, meaning that those states are accepting states. You can get multiple ones. Okay? So that's how we started with. And then we spoke about this particular set comprehension, right? If you're given some DFA, what will be the set of strings that's accepted or recognized by this particular DFA machine? And that's the mathematical detail that we spoke about. So this delta here, as you can see, this delta here, right? Delta, that's a transition function. So we got two versions of the delta. This delta here is non-recursive, meaning that every time you got a state, you can only read one character at a time. However, to really make this definition here a little bit neater, we just introduce another extended version of the delta, which will be recursive. So the way we did it was by saying, rather than just taking a single alphabet, but now we got star, that means we can have a sequence of characters to be processed at a time. Okay? So that's why we got delta over here with a hat. So that means generalized version, that's recursive. Right? So we'll talk about how we can define this delta hat over here recursively. Right? So basically, you can break down each string to be processed into the prefix and also the last character. For example, if you got 0, 1, 0 to be processed, think about this part here, the last character to be A, and the remaining part, which will be the prefix, that will be X, and etc. Right? So you can break down every input string into two parts, the last character and also the prefix. And then you can define the delta hat accordingly. Right? We spoke about it as well. And this will be the final alternative definition for the language accepted by M. So here we're just using delta hat as opposed to delta. Right? So you want to make sure you get yourself familiar with both notations. Either use the non-recursive version or the recursive version. Right? These are the two. Any questions about these two? Okay, good. And today we're going to see for NFA, we also got something similar. We also got to define for NFA, we're going to define both the delta and also delta hat. However, the situation will be more complicated. I can give you a little bit preview. So here you can see that if I try to calculate for, let's say for DFA. For DFA, if I got a single state by taking a character, because it's deterministic, it's guaranteed it's a single destination state, unique single destination state you got to go into. However, for NFA, it's non-deterministic. So this guy here, rather than a single state, is going to be a set of states. That's something we're going to see today. Right? That's an NFA. Because somehow we learned about the concept about alternative universe. So that means I got to think about how many parallel universes you have for the NFA. Okay, we'll get there. All right, so formulation for DFA, you guys can take a look. And that's an NFA, right? So this page here simply says, sometimes it might be a little bit easier for you to think about conceptually how you can specify a language using NFA. So you don't really have to specify for every state, you don't have to say here, also what's going to happen if you got 0. You don't have to. That's kind of the benefits of non-determinism that can give to you. But once you got NFA like this, it will be possible for you to convert this guy here into the corresponding DFA. And this DFA here can be somehow minimized in terms of its states, which we will talk about later. And once you got the minimum number of states for the DFA, it can be turned into... Oh. Yeah. No. I know, it happened, yeah. Might just be testing, I guess. Okay. Anyway, so given any arbitrary NFA, you will just be able to turn into DFA. Okay, so that's... Okay. Yeah, guys, if there's an emergency, you can let me know, right? In which case, we're going to do something. Okay. All right, so that was the last page that we spoke about, right? We kind of show you a movie clip, but that one there is not required for the course. I just want to show to you the connection, okay? So this will be something you want to know. So if I want to somehow trace this particular string, if I want to process 0, 0, 1, 0, 1, the way I did it is by drawing something almost like a tree to show you the branching structure for like alternative universes. But I think to really do this more precisely and also formulate the NFA concept accordingly, we had to use something different rather than just tree. Also, feel free to use this one here if you find it intuitive for you to do the tracing. We're going to see something a little bit different today. Okay, so we're still going to use the same NFA and also going to use the same string here to see how we can process it. Okay, that'll be the goal for today. All right, so let's now dive directly to the same example right here. And let's see how we can process this particular string. I think in your lecture template, I do make a typo here. I just fixed it right before the lecture. On your template, it might show 0, 0, 0, 0, 0. That's wrong. It should be 0, 0, 1, 0, 1. Yeah, you can feel free to fix it. Okay, I'll try to update the file maybe once I process your lecture recording for today. Okay. Let's now do some example here, and then we'll see how we can formulate it accordingly. Okay, so we're going to process the string one by one. Okay, let's just use different color convention. Let's say the first one, we're going to use blue. Okay, 0 over here, and then the second 0, green, and then 1, and then 0, and then 1. Let's try this one here, okay? So here's the thing. If we are trying to define a transition function for NFA, in some way NFA is very similar to DFA, okay, similar. So it also has a transition function. But the transition function here is not going to return just a single state. So you can think about here, and then you got some states over here, and also you got some input character. So this will be some source states. And this will be presumably part of the alphabets. This will be some input character or input symbol to handle. And the delta here is the transition function for NFA. And if we're talking about this, rather than returning just a single state, it's going to return a set of states. So think about this one here. It's actually going to return something that's a subset of all the states. So if you remember, the Q here in the formulation is the set of states. And we're saying that the return value from here, transition function for NFA, is going to be a subset. That's something very important, as opposed to, in the case of DFA, you would say it's a member of, as opposed to subset of, right? That's a critical difference. All right, so given this kind of a sketch, let's now try to work out this example together. So the start state is actually Q0. Okay? So here we start with Q0. Okay, so this is the beginning state. That's a start. And then we are trying to basically process 0, the first character. So 0 can either lead us back to Q0 by following this, or we can go to Q1. Okay? So the way to write it would be, let's put it here. So we got delta, and then we got our initial states, which would be Q0. And then we can process 0, which will be a set, which can be either Q0 itself or it can be Q1. Okay. Q0 itself or Q1. And the fact that we actually got this subset relationship is because of non-determinism, right? Let's just remind ourselves. So this will be non-determinism. Are we okay with the first one? Okay. Yes.
What's the subset of like set of n?
Sorry, say it again.
What's the transition function of set of? Subset of?
Q.
Oh, set of states.
And then, so to continue, so you can think about after processing 0, we can end up being in either at Q0 or Q1. So now we got to consider these two states separately. Think about this parallel universe number 1, parallel universe number 2. Handle them separately and somehow union their outcome together, because each one of them may result in another set of states. Okay, let's now try to take a look. So now we're going to handle basically 0 over here, right? It's the second one. So it's going to be delta, either the starting state could be Q0, in which case we're going to handle 0. Also, it could be delta, but the starting state could be Q1, in which case we handle the same symbol right here. Right? However, we're going to combine them together because all the possible outcomes should be included, right? Union. And then let's now try to simplify that. If I am now in Q0 and then I read 0, if I'm in Q0, read 0, it can be either the same thing or go to Q1. Q0, Q1, versus if I'm now in Q1 and then I take 0. What is that, by the way? If I'm now in Q1, but I want to process 0, I'm basically getting stuck because it's undefined. So what will be the outcome stage? Yeah, just empty.
By the way, shouldn't the transition function be a subset of the power of the states?
So here we're saying when you apply the transition function to a state and a character, and then that one there is going to return a set of states. A set of state will be a subset of this state here. It's just a different way of saying the same thing. You will see the formulation a little bit later. Yes?
For source state, can we just write it as Q0 and for input symbol as A0?
You mean Q0, A0?
Yeah.
These could be kind of like, for example, Q0 could be the start state, yes, if you do it that way. But here I'm just saying any arbitrary state S and arbitrary symbol C. That's what I'm saying. So here I'm just trying to explain that the type of the return value is not going to be a single state. It's going to be a set of states. Yeah, that's my intention here. Good. All right. And then, so here is going to be union and the empty set. Right? That one there is just going to be Q0 and then Q1. So what does that mean? That means after processing 0 and 0 up to this point here, we might be either Q0 or Q1, either way. So if we want to process another character 1 here, we're going to see what's going to happen if 1 is processed either from Q0 or Q1 and union their outcome. Right? We're going to keep doing this. For completeness, let's just continue. Okay? So we're going to process 1 right here. So our starting state here can be either Q0 or Q1. Okay? So delta Q0, but now we are trying to process 1. Union, and then we'll keep in Q1 and then 1. Right there. Now, if I'm in Q0 and then I take 1, and I'm back to here. Right? Only Q0. So that one there, basically like that. And only one possibility. That will be just Q0. Union with, if now I'm now in Q1, for example, Q1, and then take 1. It will lead me to Q2, right? Which will be Q0 and Q2. That means after processing 0, 0, 1, I could be in either Q0 or Q2. In order to process the next character 0, I should start with either Q0 or Q2, right? All right, let's now continue. Let's continue with the 0 here. So it could be delta, and then we got Q0, and then 0, union, delta, Q2, and then Q2, and then we got 0 here. Okay, let's see what each one of them will represent, and then we union them, right? So if you're now in Q0, you got 0, right? That one, basically, again, right? The same pattern. So here or here. That one will be Q0, Q1. Union. And if I'm now in Q2, I'm getting stuck. It's undefined for any input symbol, right? That'll be just empty. That means I got Q0, Q1. So after processing the first 4 characters here, I got Q0, Q1. Right? Now the final character. Let's do a little bit of preview. The final character is right here, just 1. After processing the final character, you can imagine that I will get another set over here. As long as one of the states in the final set there is an accepting state, then we should accept. Because that means one of the alternating universe will accept it. Right? All right, finally, let's process 1. So I got either Q0 and then process 1. Union, Q1, and then process 1. So Q0, process 1, just go back to Q0. Right, again, go back to itself, Q0. And then, if I'm now in Q1, process 1. Q1, process 1 will give me Q2. Q1, process 1 will give me Q2. This will give me Q0 and Q2. So we got Q0 and Q2 right here, right? So now that means after processing 0, 0, 1, 0, 1, I could be in either Q0 or Q2. As long as one of them is actually accepting, then the whole thing should be accepting. Okay? So what I would say is, let's just put this one here. Give me one moment. So this one here is a final one, right? Let's put a star here. So you can think about this Q0, Q2 intersecting with Q2 is the only accept states. It's not equal to empty. That means at least one of them is accepting. So that would mean this string over here should be accepted. 0, 0, 1, 0, 1 should be accepted. This is some condition you will see when we actually go over the language definition for NFA. We'll see that very soon. But let me just do a little bit more annotation here. So this guy here is the possible ending states. Possible states after reading the entire input string. And the Q2 over here is the accepting states. Sorry, I'm running out of space, but I'll try my best. Let me put it here. Okay, the Q2 over here is the accept states. If their intersection is not empty, then that means at least one state should be accepted. All right. On the other hand, if somehow all the possible states after processing the entire string simply has no intersection with the accept states, in that case, it should be rejected. You can definitely give a try on a different string. For example, exercise what about 0, 0, 1, 1, 1? This one here should be rejected, but show exactly how. Okay, that'll be exercise for you. Okay. All right, any question about this? somehow this example here, the way we kind of compute about the intermediate states, which is a set rather than a single state, will give us some very nice insight into how the formulation will work. So I'm kind of presenting to you this example here before we try to formulate NFA. The way we formulate NFA will be very similar to DFA. It's mainly the transition function that we got to be very careful, because it does return a set of states as opposed to just a single states. That's really the main thing we want to watch out for. All right, question? All right, let's now move on. Yeah, go ahead, please.
When we put the final states and found the intersection with the accept states, could we just say Q0, Q2 is a subset of Q2 set, including Q2?
In general,
Or the other way around?
you wouldn't want to say a subset, right? You want to make sure this is one possible final state. Okay, how about this is one possible ending state after processing everything? This is just another possibility. You want to make sure at least one possibility there is a member of the accept states. But if you only say subset, it's not general enough. So the most general way to say that would be, you can say, well, another way for you to say that, if you want. Okay, thinking this way. So let's say E will be the set of ending states after processing all input characters. It will input string. Okay, let's say. And also we got our F, which will be the set of accept states. And now the condition we want to formulate is, should an NFA accept the input string? So that's a question we're asking. So the way I presented this, like here, one way to do it would be like this. You can see whether E intersection with F is not equal to empty. That's one way. Another way to do it, you can use maybe logical quantification, for example. We can say there exists some state S. S is an ending state after processing the entire string. And also S is also happen to be accepting. Right? So these two are equivalent.
So it's too general to say F is a subset of E.
That one is too specific. It's not general enough. You might cover a certain scenario, but you wouldn't cover all the scenario.
Okay,
Yeah.
thank you.
Yeah. Yeah, apparently, well, let's say this. Yeah. So let me just, since you're asking, right? So why don't we just make it a little bit more complete for everybody too, so everybody can benefit. If you simply say E is a subset of F, this one is not going to work, because if you simply just use the example that we had earlier, right? So here, for example, here I got Q0, Q2. And over here, I got only Q2 is accepting. Apparently, this is actually false. But overall, the result should be true. Right? So apparently, this one here is actually false. But the input string should be accepted.
But I mean F as a subset of E.
F is a subset of E. That one also may not work. I tell you why. Let me try to think about something on the fly. Okay. You were asking about if you say F is a subset of E. So let's say, for example, let's say let's say either Q1 or Q2 is accepting. And then, let's say the ending states.
Oh, because there's multiple acceptance.
Yeah, could be, but could be, for example, let's say it could be Q0 and also Q2. Let's say, right? In this case, you can see the intersection part is actually here, Q2 and Q2. So input string should be accepted, but somehow if we apply your relations here for the subset, it's going to be false. It's contradicting again, right? So I think that is a very nice pattern here we are finding. So far we have seen 1 and 2 will work. However, 3 and 4, well, maybe other alternative may not work. So you got to be able to judge which one's going to work.
Sorry, can you, I'm still confused with this explanation. Yeah, I'm kind of still confused on
Which part are you confused?
like, E and F, what they're supposed, like, I know they represent a set of states, but why are we using E and F? Like, what are we using?
So you may want to maybe review about F. That's actually part of the formulation for the DFA, right? It's a set of final, like accept states.
No, I know what the states are, but like, why are we forming 1 and 2?
Why are we doing this?
Yeah.
So you want to make sure one of the ending states, after processing the entire string, is going to overlap with some accept states. So at least one of them is accepting. It's really about this one here. You want to make sure one of the states in your ending states, after processing the entire string, itself is actually accepting. If none of them is accepting, then the string should be rejected.
All right. Okay.
And I can tell you that 1 and 2 may not be the only ways to actually formulate a condition, but you got to think about different possibilities, right? You want to be able to judge. If I give you another alternative logical expression, you should really try to see which one will work and which one will not work, right? All right. If you know follow up, let's now continue. Okay. Yeah, again, after you have studied the math review lecture, I think this part here would be not so bad, right? It's just about basic logic here. Okay. And before I move on, I think let me start another page. I want to just briefly talk about a formulation you're going to see about transition function. Okay. So when we talk about transition function, okay, delta is going to be the same symbol for both the DFA and also NFA. Okay, so in the case of DFA, let me use a different color. In the case of the DFA, delta, as we learned last time, is going to be a pair. The first component in the pair is a states, and then the second one is a single character, right? And that one there is a total function, which will give you a single states. Right? Remember, there's a study question I gave to you guys last time, so maybe take a look at that. Okay? So that's a total function. And for NFA, let's put it side by side. For NFA, also delta over here, but now, given a single states, given a single character, is going to return a set of states. Because, for example, you can see that this example here, given a single states, given a single symbol, you're going to return a set of states, right? And the way to express a set of state will be using a power set. Okay? And for that one there, I also need to refer you to the review lecture about power set. You will need to look at that. Okay? If you got any trouble understanding that basic, you can let me know. We can go over outside the class. All right? So that's kind of the difference in terms of the formulation just for transition function. And that's really the essence of the difference between DFA and also NFA. And of course, potentially, you can think about, let's dive into this a little bit more. This is saying the destination are a set. And then let's think about a different possibility. If all sets of destination states are singleton sets, then that means the NFA happen to be a DFA. I'll show you one example. Okay. Okay, so what do I mean? Just a very simple example here. So let's say this is my machine. Let's say I'm trying to count the odd number of zeros, right? That's something we have seen before. So let's say we got S0, S1, and we want to accept the odd number. Okay, so 0 over here, and 0 over here, and also 1, and also 1, right? If you think about the transition function for this, if I tell you that this is an NFA, okay, how do we kind of show the transition function? Okay, I would say delta, for example, S0, and then if I read 1, is only going to give me S0. This is a singleton set. Similarly, if I try input 0, S0 and then read 0, that one is going to give me just S1. And etc. So if you try to do this for every possible state and input, you will see that the resulting state are all singleton set, a set with a single state. If your NFA is going to give you the resulting sets, all being singleton set, it just happened to be DFA, right? That's the property I'm trying to carry over to you. All right, that's number one. And number two, that one is kind of obvious, but I'll just write it down anyway. So number two, when the destination states, I would just say destination D, okay, just destination. Either D cardinality is simply 0. That means you get stuck, right? You just have nowhere to go. Or the destination somehow is strictly larger than 1. That means it's not singleton either. In that way, you do have non-determinism. Okay, let's refer back to this NFA very quickly. For example, you can see that, let's say for this Q1 here, what would be the transition function applying to Q1 with 0? Empty set. You get stuck, basically. On the other hand, here, if I got Q0 here, if I want to read 0, I can either get to Q0 or Q1. So the cardinality of the resulting set is 2, also strictly larger than 1, right? So either way, you have the non-determinism. Either when you get stuck, or you got multiple possible resulting states after processing this input character. Right? Yeah, some very nice little property here to show to you what we really mean by non-determinism. Okay? You just don't get a singleton set, like a unique destination to go. All right, so try to compare these two, right, about DFA and also NFA. Okay? And then what we should do now is to formulate the NFA. Let's do that, and then we'll take a short break. Okay? You know what? We're about halfway right now. Why don't we take a short break, and then when we come back, we'll do the formulation. That may be a little bit better. Okay? All right, so before we get to the formulation, I think one of your fellow students asked a very good question during the break. I just want to clarify that. That's something on my notes anyway, so it's good to mention that right away. So when we compare DFA and NFA, you want to think about which one is more specific, more specialized, and which one is actually more general. Okay? Again, we can use the little diagram that we can use to kind of illustrate such a relationship. Okay, I'll get right to the point. Okay? if I say I want to consider all the machines, the set of all the machines, DFA, NFA, okay, I'll put it here. Let's say DFA represent the set of all deterministic finite automata, okay? On the other hand, I got NFA will be the set of all non-deterministic finite automata, right? Let's say we got two sets over here. Somehow, I will be able to draw this diagram right here. Right? If I want to compare two sets. So there's one particular relationship, I can say the purple one there is actually much more general. And the green one here is much more specialized. Now the question is, which one should be the green one? Right?
DFA.
Aha, that's good. That's correct answer. Okay, but let's put it down first, right? Of course, we don't try to memorize. We try to kind of understand the reasoning. Okay, this guy here will be DFA, and this guy here will be NFA. Right? Well, remember what we said earlier. DFA are simply the kind of NFA where, so basically every DFA is an NFA, but not every NFA is a DFA, if you see the diagram. Okay? DFA are just those NFA where the resulting sets from processing each input symbol is a singleton set. So this actually links back to the point that we actually mentioned before the break, right? I just want to present that in a slightly different angle. And then NFA over here, basically, there's got to be a machine that's actually NFA but not DFA. Apparently, that's when you actually got either the resulting set is actually a cardinality 0 or cardinality more than 1, right? That's where the non-determinism comes. Basically, this is a NFA with non-determinism. It could be the resulting sets will just be empty. Or it could be that the resulting set has more than one states. Right? Either way, right? So that's a typical NFA. That's actually not a DFA, right? I think this one just somehow gives you a little bit more insight into the difference between these two. Okay?
What is the green text?
Which one?
The green text.
Sorry, you cannot read it? Or
Yeah, I can.
those NFAs where the resulting sets from processing each input symbol is a singleton set. Good. All right, let's now talk about formulation. Okay, and the formulation there, I'll just give you guys maybe just a link to the example that we just did. And I wouldn't emphasize too much about it, but it should be quite straightforward. But I'll just give you guys some guidance about reading the math. But you guys can spend some time after the class and then let me know if you got trouble understanding it. I'll try to do as much as I can. All right? So this is the example that we just did from scratch before the break. Right? I'm going to link this example to the formulation. It will help. Okay? So we're going to do two things for formulation. Oh, just before that, sorry. So NFA is just another machine. So we got Q, we got sigma, we got Q0 and F. So these are just identical to how we formulated DFA. So that one there, I wouldn't repeat. You can also look at the slides for the precise definition. What's really going to be the difference will be the delta. Okay. However, here for delta, we're just going to go directly to delta hat, like a generalized version, where you can see that we are reading an input string rather than input character. Okay, that's what we're doing here. And how exactly can we define this recursive transition function? Okay. So this is the generalized transition function. Delta that takes as input a string rather than just a simple character. Okay? And then it's going to return a set of states. Okay? The way we're going to define this one here recursively, similar. Base case would be if we are in a particular state Q, which could be the start state, could be somewhere in the middle, just some states. If I have not processed anything, it could be just the state itself. But now, the return value from the sigma, the return value from delta hat is going to be a single state. So rather than saying just Q, I'm going to say Q in a set. That's more like a base case. So the only difference is if you look at the base case, back in the DFA case, we just don't have the set symbol, right? But now in NFA, it's going to be a set of states. So that's why I put Q here in the states. So this will be the base case. Now the recursive case is very interesting. Then before I write down the definition there, I want you to somehow recall how we did the tracing before the break by using the example. Okay? The way we kind of define the recursive case, similar. So we say that we break down the string into the prefix, and also we got also the last character. Okay? So the purple one here is the last character, the last symbol. And the X over here is really the prefix. Let's try to find the correspondence right away in the example. Before we were trying to process 00101, the last character apparently is 1, right? So you can think about this one here is our A. Last character, which is 1. On the other hand, we also got the prefix, everything but the last character, which will be 0010. That'll be X. Right? And remember what we said earlier, after processing 0010, the resulting state is Q0, Q1. And then from there, we got to make sure we actually got a starting point, both the Q0 and Q1. So you can see the Q0 here and Q1 right here. Right? So that's the insight into the formulation. Okay? You have to think about after processing the prefix of any arbitrary string, you're going to end up in a set of states. And for each member of that set of states, you're going to work out what's going to be the outcome from the last character processing. Okay? That's something we're going to see. Okay, let me just visualize this quickly, and then I'll write down what we're going to do. So first of all, let me start with this. So here I got the delta hat. And then here, I start with Q0. Okay, I'm trying to handle this string here. Q0. 00101. Okay, and then we are trying to say this one here is X, and this one here is A. Okay, X and A. And the way to do this is we're actually going, so in this case, let's make it a little bit more specific, because we know that resulting state is simply Q0, Q1, just 2, right? So what we should do is, so this will be simply equal to delta, and then, so hat 0010. Oh, beg your pardon. Now I know what to write. So here I got Q0 here, 0010. However, over here we know that this here can give us, after 0010, right, 0010, it can give us either Q0 or Q1. So this one here is either Q0 or Q1. So I cannot really apply delta directly on this, because delta should be applied to a single state, but not a set of states, right? So I'm just going to remove this one from here. So what I should do instead is to somehow introduce some intermediate variable. That's what you will see in the formulation. So let's say we got something called Q prime. Right? Because it can be a sort of set of states. Q prime is going to be the starting point to handle the last character, which can be either Q0 or Q1. So thinking this way. So I start with Q0 here. And then after processing 0010, I can be either in Q0 or I can be in Q1. Right? So I'm just calling each one of them just Q prime. So Q prime can either be this or that. From each one of them, I just need to apply the final one. So from Q0 here, I want to know what's going to happen if I process the last character 1. And from Q1 over here, I'm going to process the last character 1 as well. And that one there is going to be this one here and also this one here, right? So this one here can be Q0, Q1, and this one can be just Q2. And then I'm just going to union them together, right? So this Q prime here is really something you're going to see in the formulation, right? So let's now, given this kind of informal sketch visually, let's now see the formulation, okay? So let's see this recursive case, okay? I'm just going to put it here. Recursive case, okay? So here, the delta hat, so Q and then XA will be equal to. Ultimately, I should really union as many sets as I need to. If I only got Q0, Q1, I need to union 2 sets. If I got Q0, Q1, maybe another state, I need to union 1 to maybe another one as well, right? Depending on how many I got. So what we really need is something called generalized union. Have you guys seen this symbol before? Maybe I mentioned that very quickly. Generalized union. Okay, so now if I got something like, for example, like if I got A, B union, and also B, C union, C, D. This will be, if you like, you can put a generalized union symbol, like a big U. And then it's going to union a set of sets. And then I'm just going to put 1, 2, and 3 inside. A, B, B, C, and also C, D. They will give you just the same result. So this is a generalized union you will see in the formulation, because in general, we simply don't know how many intermediate states there are after processing the prefix. It could be 2, can be 3, can be 4, right? All right. Once we got this, let's now see the formulation. Okay. All right, so let's get back to here. Okay. So this one here is going to be a set comprehension, first of all. So we're going to get here and here. So think about, we got some Q prime. So the Q prime here is actually after we have processed the X. So Q prime is exactly a member of the delta hat processing X. And by the way, the Q here is the start states. Okay? And then the Q prime here is actually just can be Q0, Q1. But once you got Q prime, you got to apply the last step. The last step will be just a regular delta, and then you got Q prime, and then A. And A here will just be the last character of the input. Okay? But if you only write this one here, it's not going to be valid mathematical expression because this guy over here is a set. Exactly the situation we have. You can have individual sets over here, but ultimately you want to flatten out the structure. Right? You want to get maybe just A, B, C, D as a set. But how do you get that? You're going to use a generalized union. Okay? That's something you guys will have to dive into. Okay? A, B, and C, D. Okay? So that's why in the actual formulation you will see generalized union. That's what you will see. Okay? But in the slides you will definitely see the cleaner version. I mean, I just try to derive the formulation together with you. But you will definitely see the complete version as well in the slides. All right, finally, let's now take a look at this one here, right? Once we have got the delta hat, let's now can define a language. Very similar, okay? The language that's accepted by some NFA M is going to be all the strings, W, and W must be, each individual character must be a valid alphabet. And also, if I try the delta hat, the recursive version, I'll start with the start states. And then I try to go with the entire string. That one there is actually going to give me a set of states. And here, I basically go back to this problem here, right? I can go either 1 or 2, right? Okay, for that one there. So I would say here, intersection with F is not equal to empty. All right? Yeah, just dive into the formulation when you study for the slides, but hopefully we already covered all the insights you're supposed to know. Any questions about this? We're good? Okay. Okay, I would suggest at least we cover one more example here, and we're going to see how we can convert from NFA into DFA. Okay. Sorry, I didn't hear you. So the M here is the NFA. It's not DFA. Because now we are talking about a formulation for NFA. Is that what you're asking? Yeah. Okay, so let's now talk about this conversion. And the one we're going to use is something called lazy evaluation, which means we are only going to create new states for the DFA when necessary. Okay, so given some NFA, let's start with the one we already got, before the break. Let's start with that and see how we can convert that into a DFA. Okay, it's something called lazy evaluation. There is some pseudocode that we can also dive into, but I'll leave that maybe to next week. Okay, but today let's focus on this example here. Okay. So just to start with, you can see given this NFA here, apparently the Q will be all the states. Q0, Q1, and Q2. And the initial state, Q0, just happen to be just Q0. I'll just call it Q0. All right. And we're going to use something called lazy evaluation. Lazy evaluation in the sense that you only create a new DFA states when necessary. Create a states for the final DFA only when necessary. And when I say when necessary, that means it's somehow reachable. We'll see exactly what I mean by reachable. All right, let's just go by example. Always, you want to start with the start states, Q0. But the way you put it, you don't simply just put Q0. Because we got to work with the set of states for the NFA to really accommodate for non-determinism. So notice that you got to say, start with a singleton set. Okay, so this will be the starting point. So this will be the start states of the resulting DFA. You want to think about every state in the ultimate DFA is going to be like a set of states from NFA. Okay, I'll write it down here. So when we say we want to do conversion right here, each states in the resulting DFA corresponds to a set of states in the input NFA. Right? It's a very important property right here. All right? So this is a set of states in the input NFA, and that one corresponds to just a single state in the ultimate DFA. Okay? And then from there, so there's only one possibility for us to look at. We want to see for every state in the set, what will be the resulting set of states by processing input 0 and input 1, because we got alphabet 0 and 1. Okay? Let's now apply the transition function. Okay? So for this one here, I'm going to say delta Q0, there's only 1, and then 0. Also delta Q0, and then 1. Right, you can see the 0 here, 1 here, 1 here, and the Q0 here, and the Q0 here. Just correspond to the Q0 here. Yeah, for this one we know pretty well, right? If I and Q0, reading 0 is going to be either Q0 or Q1. And this one here is going to be, if I'm Q0, I read 1 will be Q0. Now, these two sets belong to different semantic categories. This one here is something we got to explore further. It's like a newly discovered states that we have to see how they can be transitioned into. But this one here, Q0, simply just corresponds to something we already know about. So think about what we're doing here. I'll also show you some visual, right? Imagine that we are trying to construct the DFA on the fly. When we first did this, we start with the DFA right here. And then we got Q0 right here. That's how we start with. Okay? And then this one here in some way tells me that if I process 1, I will just go back to itself. Meaning that processing 1 is not going to lead me to any state I haven't explored yet. On the other hand, Q0, Q1 is a new state I must explore. Okay? If I do 0 over here, that one is going to lead me to Q0, Q1. And for this particular subset state over here, I don't really know what's going to happen if I got 0 and what's going to happen if I got 1. I need to figure out. So that means that one there deserves another row right here. But for this one here, Q0, I already know what's going to be the definition. Right? So that's a very important concept over here. So this one here is to be discovered. And Q1 over here is already discovered. All right. Let's now draw a line here. So now, that's lazy evaluation. We only create a new states when necessary. So what I would do is I'm going to put this one here. So let me say that one's pink. Okay, that's a new state. And the green one here just corresponds to something I already know, right? Q0. So I'm going to put that there. So Q0, Q1. That will be something I want to discover right away. So over there, I got to handle Q0, Q1, right? So now we do need a union. So delta, either Q0, I handle 0. Union with delta, I can be Q1 and also 0. All right, notice the correspondence. Either Q0 or Q1 can be the starting point. In both cases, I'm trying to think about how to handle 0. Right? Right, let's now try to calculate this quickly. Q0, 0, well, Q0, Q1, right? Union, Q1, 0, Q1, 0, empty, right? Which will be equal to Q0, Q1. All right. Q0, Q1, luckily, is repeating itself. That's been discovered already. All right, let's see the next column. And we still got to do delta, but we're going to say Q0, but handle 1. Union, and then Q1, and then 1. Right? 1 here, so that's why we got 1 here. Q0, Q1, Q0, Q1. That will be Q0, you read 1, just Q0, singleton set. Union. And if you got Q1 over here, you got 1. Q1 here, 1, you got Q2. Q2. That will give you Q0, Q2. And we haven't got Q2, Q0, Q2 just yet. That's something to be discovered. Another color. All right. So what we have done so far was from over here, from Q0, Q1, if I read 0, it's like that. But if I read if I read 1, it's going to go to another state here that represents Q0, Q2. Right here. I'll put a 0 right here, right? And now we ought to explore this one here. Okay, let's see. Okay, I think I might just need to make everything a little bit smaller so that I got one more row. Okay, I might just be able to do this. There we go. Okay, now I have space for one more row. I can tell you there are only 3 rows we need, ultimately, right? I know the answer, so. Okay, so here we got one more row. Right here, and then here. Okay, one more row. And that one there is going to be Q0, Q2. Okay, so we actually got Q0, Q2 over there. Q0, Q2. Okay, right here. Right, exactly this. And then, let's now try to do that. So now we got delta Q0, Q2. So Q0, we read 0. Union, delta, Q2, and then 0. Guys, what's the answer? Q0, 0 is going to give us Q0 and Q1. And then Q2, 0 will be empty, right? So that should be just Q0, Q1, right? And that one is awesome because that one there is corresponding to something we knew already, right? So now we can do right away Q0, Q2, If I read 0, it's going to go back to Q0, Q1. Q0, Q1, right? 0 here. And by the way, that's 1. Okay? And the final cell to really figure out is right here. Okay? Let's do it. So delta, I got either Q0 and then 1 union Q2 and then 1. All right, let's try that. Q0, if I read 1, just Q0 itself. If I now in Q2, read 1, empty, just Q0. Agree? So that one there would just be Q0. That one there is exactly the Q0 here. So that means after reading 1, I will go back to right here. All right? Now, one more step. This will be almost like the DFA we need to, but you can see currently the DFA here has no accepting states. So which one should we accept? Basically, any of the subset states where we got 1 accept states. Okay? Accept state is Q2. Where can we find Q2? Right here. You can see Q2 over here is a member of F. So that means this particular subset state should be considered as accepting. This one here. Right, the diagram on your slide is actually neater, but I'm just trying to show you the whole process. Let me recap quickly. The problem is, given some NFA, we want to convert it into an equivalent DFA. That's the problem. The way to do it is by something called lazy evaluation. You always start with a set of states, a singleton set of states, that will contain just the start states for the NFA, which is Q0 in this case. And then you're going to start building the table. You will add a new row only when necessary. Whenever you construct the resulting set of states, if that set of states is already part of the row you have built, you don't need to do any new row. But let's say in this case, Q0, Q1 is not there just yet. So that's why you got to add a new row for that. All right? I guess this might be something you did, maybe in 2001, but it's good to brush up, right? Because once we have done this, next time we're going to see if you actually introduce epsilon transition, how can you actually do something very similar, all right? All right, so make sure you can do given an NFA, and that's a DFA. Right? Also deciding which one should be the accept states, right? So that'll be something for you to look at. Yeah, so everything I've said here, also on the slides, I'm just trying to build an example together with you. You can easily find the corresponding slides, okay? All right, guys, any questions about this? All right, so I'll end the class a bit earlier today. So next time, we're going to start with reviewing this example here and see how we can look at a pseudocode for this algorithm to see more insight. All right, thank you. I'll see you next week.